All right. Well, hello and welcome back to the lectures, this time on section 5.3. Today, as you know from the PowerPoint slides, we're going to be talking about truth tables, or more specifically, ordinary truth tables, and what they can be used for, or in other words, what they are good for. And so you already know, having looked at section 5.1 and 5.2, how to take a statement in English and then translate it into the symbols of propositional logic. And then that was 5.1. And then in 5.2, how to apply the truth tables for the propositional operators in order to determine if, say, some statement like this is true or false. We're going to take that a step further today now in 5.3 because we're going to be talking about an ordinary truth table. And before I explain, sort of what's going on with ordinary truth tables, I wanted to show you how to set one up and just go through the procedural aspects of constructing an ordinary truth table, and then we'll talk about what's going on here. So I'm not going to be projecting the PowerPoint slides as I often have over here because there's just not that much information there, and I can then use this board space here more efficiently. So, having said that, as you know, you can look at the PowerPoint slides, and the first thing I'm talking about there in 5.3 is to look at the number of different letters that you might be dealing with in a given statement. So obviously in this case we're dealing with two different letters, and so what you want to do is over here to the left hand side you're going to list all of those different letters. So in other words, A and B, and you'll see here as we proceed today that we'll eventually get the letter C thrown in. We'll have three different letters and we'll go from there. But you just list all the different letters over here that are found in this statement. Now, we're doing a table, so we need to have columns and rows, and we can probably fairly intuitively understand that, speaking of columns, we'll have a column underneath each of these letters. We can have a column underneath these different operators. But what we need to know is how many rows we're going to have in this truth table. And so, to be clear here, there's a formula, and it is 2 to the n. So 2 to the power of n, where n is the number of different letters here in your given statement. So in this case, we'll be talking about 2 squared, which of course is 4. That's the number of rows that we will have in our truth table. Again, as you will see in a few minutes, we'll have a statement with 3 different letters. Move out of the way so you can see that better. 3 different letters, and in that case, we would have a truth table with 8 rows in it. And obviously, this is going to increase literally exponentially. And so if you had 2 to the 4th power, so dealing with 4 different letters in a statement, you would have now 16 rows in your truth table, and so on. I will go ahead and let you know now, since I'm thinking about it, and so you don't have to worry too much as these numbers increase fairly quickly, that at least in terms of the exam that you'll have on Chapter 5, I won't ask you to go beyond an 8-row truth table, right? So at the most you'll see 3 different letters in a given statement, meaning that you would have 8 rows in your ordinary truth table. Now in the book you will see some that have 16 rows that go beyond that. Don't be intimidated by that, and certainly don't shy away from doing problems with 4 different letters here, because it's not that these are more difficult than these other variations, I guess we could say, of ordinary truth tables. It's simply that there's more of it, right? It's just a longer problem. It's not a more difficult problem. So at any rate, we know that we will be dealing with here a 4-row truth table. And so what we're going to do is we're going to come back over here. And once you know how many rows you're going to have in your truth table, you always want to start on the left-hand column here, in this case under the letter A. And you want to make the first half true. So if we have 4 rows, we'll have 2 trues, followed by 2 falses. That's the pattern that you want to establish here. 4 rows will give you 2 trues, 2 falses, and then with every column that you move over to the right, you want to split that in half. So if you had 2 trues and 2 falses, you'll have 1 true, 1 false, and then repeat to fill up the table, or in other words, to go for 4 rows, as we saw. And so what we have come up with here is what I like to call a pool of values, a pool of values. I'll go ahead and erase this so I'm not standing behind that all the time. So that is a pool of values. And what this ordinary truth table does, and what this pool of values does, is give us all of the possible combinations of true and false for these two different letters, right? So obviously we have the combination where they're both true. We have the combination where they're both false. We have the combination where the A is true and the B is false, and then vice versa. And so that's why you want to follow this pattern precisely, because this will always give you all of those combinations. And that's what really we're investigating here with an ordinary truth table. That is, how does this statement here turn out for all the different combinations of true and false, right? In 5.2, which you just looked at, you're told in the instructions, well, let A be true, let's say, and let B be true, and then you work out, well, how does that turn out? And so on. But here we're simply going to, instead of being told in the instructions what values to plug in for A and B here, get that from our pool of values. So having said that, hopefully that gives you some context here for what we're doing. Having said that, what you want to do then is, before you start plugging in this pool of values into your statement over here, this is a crucial step for everything in Chapter 5. That is, you want to identify the main operator of the statement here that you're dealing with. Now, obviously, we only have two operators, the wedge and the horseshoe. And the main operator, then, will be defined by these parentheses, right? It tells us that, in fact, the main operator is here underneath the horseshoe. So I'm going to go ahead and circle that, or rectangle it, as it were. You need to make this, and this is important for that first exam, you need to make the main operator column absolutely clear on any ordinary truth table that you will be working on for that exam. Because if you don't make that main operator column clear, you don't really have an answer there. You just have a bunch of T's and F's, as you will see. But we need to make sure the answer, so to speak, stands out. And so you will always identify that. In this case, this is how I'll be doing it. So having done that, we can go ahead and proceed. And simply, we're going to be doing what we did in 5.2. We're simply going to take the truth values from this pool of values here and plug them in. So in other words, we see here that based on this pool of values, A and B are both true, and so we simply take that and plug that in where we find them. Once we've done that, right, we're going to save the main operator column for last, like we saw in 5.2, and so we're going to work out true, wedge, true, right? That's what we're dealing with right here. Let me highlight that a little bit. Right? The A and the B are going to be plugged into that operator there. And so true, wedge, true, as you know from those truth tables for the wedge, will be true. Then we've saved the main operator column for last. Whatever value we come up with last over here will be plugged in to the main operator, right? So it's this wedge value that gets plugged into the horseshoe. And so what we're looking at here underneath the horseshoe is true, horseshoe, true. And true, horseshoe, true is, you just look this up from the truth table for that operator, true, horseshoe, true is true. And so we find here that when A and B are both true statements, this statement overall will be a true statement. That's what we have just shown. I want to, I guess, reassure you that what we have just done here will be the most difficult thing we will do in 5.3. In other words, making sure we've got that order of operations down and have applied it correctly to figure out the main operator value for this statement. And to just emphasize that point, just to show you the next step here, what you're going to do is go to the second row. And now we learn in the second row that A is true, but B is false. And we plug it in across the way. And since we just determined the order of operations in our first row here, we simply repeat the same pattern here. So in other words, we're looking at true, wedge, false. And so we think about, well, when you have true on the left, false on the right, what does the wedge give you? And so hopefully you remember that, in fact, it's true, but in fact, anytime you have true feeding into the wedge, that wedge is true. Anytime you have true feeding into the wedge is true. So now we end up with our main operator. True, horseshoe, true. Well, we know what that is because we just saw what that was in the previous row. That is true again. So, starting to pick up the idea here, I hope. We go to the third row, in which case A is false and B is true. And again, we plug those values in across the way. And so now we're looking at false, wedge, true. False, wedge, true is, again, true. because you have true feeding into the wedge. That makes it true. And so now we have true, horseshoe, false, right? And I'm hoping that that's the one combination for the horseshoe that really stands out to you, that jumps out. Because when you have true on the left and false on the right, a horseshoe will be false. In fact, that is the only way to make the horseshoe false. Finally, we have a last row here where both A and B are false. And you might think, well, if false is being plugged in there, shouldn't we get false in the end? But we have to find out. So let's see. We have false, wedge, false. And so hopefully that will be the combination that stands out to you about the wedge. False, wedge, false is the only way to make the wedge false. And so now, false, horseshoe, false. Yes, it's false on both sides of the horseshoe. However, as we know from 5.2, when you have false on both sides of that horseshoe, the horseshoe is actually true. So we have now found, and this is the point of 5.3, that for this statement here, A wedge B horseshoe A, we have now found when that statement will be true and when it will be false, right? It just depends on what you're plugging in here for A and B. And so we can come to the next part of 5.2, which is what mostly 5.2 is dealing with, and that is applying definitions to what we discover here, what we determine using this ordinary truth table. And so you can look at this in the PowerPoint slides. You can look at it basically in the book, of course. So having said that, the first definition we can apply to this single statement is when we have some true and some false underneath the main operator column here, as we do, we call this a contingent statement. That is called a contingent statement. Now, there are other possibilities, though, right? There's the possibility where we have all true underneath the main operator. And when that happens, we would call that something else. We call that a tautology. But you might be wondering, well, what would that look like? Well, let me give you an example here. So here's another statement, A wedge tilde A, right? Now, this is not a profound statement. This is a statement like, today is Monday or it's not Monday, right? It's hard to disagree with that. Nonetheless, what if we work out the truth table for this? A, of course, is our only letter here, so A is either true or false. We don't need to go through the exponent thing on that, I think. We have the main operator of the wedge. A is true. A is true. Tilde now, right? You'll remember that what the tilde does is it takes the truth value and flips it to the other one. So true, wedge, false is what's going to be feeding into that main operator here. That's what we have in the main operator. So this is important. This tilde value is feeding into the wedge as well as the A there. And so we get true, wedge, false, which is true, right? Anytime we have true feeding into the wedge, it's true. When A is false, the tilde makes it true. So we're looking at false, wedge, true. Well, again, that will be true, right? So what we're finding here is that this statement, A wedge tilde A, it cannot possibly be false, right? It's always true. And when you see that, you call that a tautology. It's a fancy word, we might say, but it is what we would call a statement that is always true. There's one more definition here to apply. Let me illustrate that with a slight adjustment here. All right. What if I told you that today was Monday and it's not Monday? Now that's a bizarre statement. Hard to think about that one unless you want to meditate, perhaps, achieve enlightenment. Go for it. At any rate, today is Monday and not Monday. We would, of course, have the same values for A here in our truth table. What we'd be looking at then would be true dot false. Well, true dot false is false. And what you want to remember, of course, is that anytime there's false feeding into a dot, the dot is false. False dot true. Well, we've got false feeding into a dot, and so the dot is false. And of course, what this all means then is that this is a statement, obviously, that cannot possibly be true. It's always false, as we see here. We have a word for that. As you see, this is called a self-contradiction, a self-contradiction.